Over the past few lectures, we've been looking at evaluation, and in particular at how to implement eval and apply in a language, such as scheme, in order to define a language, scheme or some variation thereof. What we've seen is that by creating or specifying eval and its associated procedures, we actually define the semantics of a language, what it means to determine an expression's value or to associate meanings with actual expressions in the language. We've also separated out the semantics of eval and apply from the syntax of the language, meaning how we choose to write the expressions can be interfaced through a data abstraction into the actual evaluation of meaning associated with those expressions. In this lecture, we're going to look at variations on scheme. We're going to explore the idea of how, by making changes, in many cases very small changes, but in making changes to eval and apply, we can cause the language to behave in a very, very different fashion. And we're going to look at how we gain some benefits, sometimes at a little cost, by making those changes, trading off design issues in the language for performance issues in actually using the language. To set the stage for what we're about to do, let's remind ourselves of what normal scheme does. Remember, we said much earlier in the term that scheme is basically an applicative order language. That means when evaluating a combination, we first evaluate all the arguments, reduce those down to actual values, including the first argument, which in our language or our syntax actually is the operator, and then we apply that operator, the procedure associated with that first argument, to the values of all the other arguments. We apply the procedure to the values. Now, while we've been accepting that as our method of operation in scheme, in fact it's a design choice. It was a choice that was made by the people who created the language. There's another way, at least one other way of looking at that, and that's called normal order evaluation. In normal order evaluation, we'd do the following. When given a compound expression, we'd say, go ahead and apply the operator, that is, the value of the first sub-expression, but with unevaluated argument sub-expressions. Or said differently, when given a compound expression, we could evaluate the first one, but then simply take the other pieces and substitute them into the body of the procedure, and do that until we actually need the value. And in fact, we would evaluate a sub-expression only when the value was needed to print something out, or because a primitive procedure is going to be applied. That is, the primitive procedures are going to be strict in requiring that their arguments actually have values. Said differently, normal order would have a very different substitution model, in which, in essence, we would take the sub-expressions, substitute them into the body of the procedure, and keep doing that substitution until we have an expression that involves only primitive procedures and their application. Our goal here is to say, how is that different in terms of how the language evolves, and how can we create such a language? To visualize the difference between these two kinds of evaluations, let's look at an example. Here's an example using applicative order, meaning the normal kind of scheme thing. Let's define foo to be a procedure of one argument x, and inside the body we'll write out a particular expression to tell us we're inside of foo, and then we'll add x to x. And let's see what happens if we call foo with an argument that has a sequence of things. And the argument says, write out the fact that I'm evaluating the argument, and then return the value 222. Now, what happens if we do applicative order here? Well, in normal scheme, or applicative order scheme, the first thing we do is evaluate each of the arguments. We'll get the value of foo, that's going to be a procedure of some sort, but then we have to evaluate this argument. We have to evaluate this begin statement. And that is going to lead to the following kind of behavior. Evaluating this argument says evaluate this begin statement, and therefore we evaluate the first sub-expression, which writes out on the screen eval arg. We then evaluate the second argument, or the second expression rather, 222, and since this is the last sub-expression in this begin, that's the value we return as the value of the overall argument. That's the value we're going to use in the application of foo. Great, so now we apply the procedure named foo to that argument 222. And by substitution model, that says we substitute 222 in for x everywhere in the body, then evaluate the body. And that says we'll evaluate this begin statement, a sequence of write out the line saying I'm inside foo, followed by evaluating plus 222, 222. Yes, I know we should really use the environment model here, but substitution is sufficient to see what we're doing. And of course, evaluating this in order says we first write out the fact that we're inside foo, and then we go ahead and do the actual addition of adding 222 to 222, giving us out the answer we expect. So let's summarize what we did. We first evaluated the argument, then substituted that value into the body of the procedure. And this led to the behavior in which we've said we've evaluated the argument once, that was our marker on the screen, then we were inside foo, then we returned the value. Keep that in mind as we now go to the alternative model. Now, let's think of the alternative model. This is a normal order model in which we're going to first evaluate the procedure, to get out the thing we're dealing with, but then the arguments we're simply going to substitute into the body of that procedure and keep unwinding the evaluations until we get down to things that either involve printouts or just primitive operations. Same definition of foo, same call, but what's the difference now? Well, in this case, we take that entire argument, we get the value of foo, but we substitute that entire argument in every place in the body of foo we see x, which says that now we're going to turn this evaluation into an evaluation of a begin that does the right line inside foo, that's the first part of the body of foo, and then everywhere we saw an x, we're substituting in that expression. Notice we've done no evaluation yet, we've simply substituted it directly into the body. Therefore, nothing is printed out, we're simply reducing to this evaluation. In this case, we evaluate these expressions in order. So we first evaluate the line that says we're inside foo, and that gets printed out. Then we turn to the next sub-expression in the begin, the plus. And the plus we know is, of course, a primitive thing, so we're going to, in this case, have to actually evaluate the arguments. We can't simply substitute them in because there's no compound procedure here. So we, in this case, now evaluate the first of those two begin expressions, which says write out the line I'm inside the argument, then get the value 222 and return it. Do the same thing for the second argument to plus, since it's a primitive procedure. Then actually apply that primitive procedure to the two arguments, 222, 222, returning out the value we expect. And now we see there's a difference. Remember in the previous case, the applicative order case, what happened? We first evaluated the argument. So we printed out, in fact, eval_arg. We did it once, because we then substituted that value into the body and applied the procedure, in which case we said we're now inside foo and we return the result. Here, it's as we said, it's as if we substituted the unevaluated expression into the body of the procedure. So now, we only first get inside of foo, writing out we're inside foo, and then we go ahead, when required by a primitive procedure, to do the actual evaluation of the argument. And of course here we have to do it twice, because we have to evaluate each argument that was substituted in before returning the result. Our goal then is to say, normal order is a different behavior. It's substitute until required to evaluate, as opposed to applicative order, which says get the value and then apply. Our goal now is to see two things. One, why is that a useful change to make? And two, how do we change the evaluator to actually accomplish that? Well, let's deal with the second one first. What changes should we make to eval and apply, the eval and apply we've grown to know and love, in order to implement this new idea, this idea of normal order evaluation, or sometimes called lazy evaluation. And of course it's called lazy evaluation because we're only evaluating the arguments when required, either because we need to print them out or because we're down to a primitive procedure application. So let's look at the changes we need to make. Well, let's start here. And here means when we're applying a compound procedure, that is, we're applying one of these things we built with a lambda, what do we want to do? We know we want to evaluate the body of that procedure in a new environment. But what should the environment do? It should take the set of parameters of the procedure, but glue together with them not the actual arguments we want to get, but a list of delayed arguments. So what do we mean by a delayed argument? Well, let's create a structure that lets us hold off actually getting the value of the argument. That makes sense if you think about our example. We want to apply a procedure to a set of arguments. What that says we want to do is, in fact, say, gee, just take those arguments and substitute them into the body when necessary, but don't actually get their values. So our change in a compound procedure says we'll still evaluate the body of a procedure in a new environment, but rather than binding the parameters of the procedure to their actual arguments, we'll bind them to this special structure that keeps track of the expression to be evaluated when required, plus, of course, we're going to need to have the environment in which we want to do that evaluation. Actually, that last point is worth stressing because it's a change. Remember, prior to this, apply didn't need to know about its environment. We simply applied a procedure to a set of arguments because in those cases we had values available. Here, we're saying we're going to delay. We're going to be lazy. We're going to hold off getting the value of the arguments to a procedure. But of course, ultimately, we want those values relative to the environment we started with. So we're going to need to pass that down. And that says we need to change, in fact, what happens inside of our apply to pass the environment in as an argument. Okay, so with this change, when we deal with compound procedures, we'll do the thing we want. That is, we'll delay actually getting the value of the arguments. We're going to have to build the structure for listed delayed arguments. We'll do that in a second, but we can conceptualize that it simply takes the arguments as expressions and glues them together with something that marks them as a thing to be done later. Ultimately, though, we're going to get down to a primitive application. And in that case, we said we wanted to do the actual work. When we got down to applying a primitive procedure, we wanted to get the actual values out. So our other change will be to say when we get down to that stage, we'll take the set of arguments in and actually get their values. That is, we'll force them to be evaluated at that stage. And here again, we'll need to pass the environment into this procedure because we're going to have to walk our way down this set of arguments asking for the actual value of that argument expression with respect to an environment. So notice then, small number of changes. Apply is now taking in an environment as an argument, and when we apply a compound procedure, we're simply building this thing that constructs a list of delayed arguments. We may have buried some work underneath there, although we'll see shortly that's not true. And then when we apply a primitive procedure, we're going to have to construct out the list of the actual argument values, forcing the evaluation of those arguments at this stage. Otherwise, very small set of changes. What else do we have to change? Well, of course, we've changed apply. We're calling it lapply here for lazy apply, as you might have already figured out. We've changed apply, so we have to change how it's used. But in fact, most of the work is now in apply. We need to call it with the actual value of the operator, but just the expressions for the operands and the environment. So our change to eval is very simple. When we get to an application, we pass in the environment as the third argument. We need to get the actual values of the operator. So we're going to have to do some work there to say get the value, do the work to get the value out. But notice, we simply take the operands as a tree structure and pass them into apply. We're just passing the expressions down. Notice that this is the only change to eval. All of the other expressions, the special forms and the primitives are going to be exactly the same. It's only in the application that we change it. And to say it one more time, we're going to get the actual value of the operator. We're going to do the evaluation. We'll define actual value in a second. We're going to simply pass the operands as expressions down to apply, and we pass the environment along as well. Apply, as we just saw, will take those operands and either force their evaluation if we need them for a primitive application, or otherwise just make up a list of delayed arguments if we're doing a compound expression. Now, what else do we need? Well, notice we've now made a distinction between getting the actual value of an expression versus simply delaying it out. As we said, when we get to primitive applications, we'll need the value. We'll need the value as well for the operator. Everything else we want to delay. But we've introduced two different kinds of expressions now, or if you like, two different kinds of values. Something that is the actual value of the expression, and something that is more like a promise to get the value when asked for it. We need to implement those, and we'll do that as follows. First, to get the actual value of an expression with respect to an environment, well, we might expect that that simply says go off and evaluate it. And that's certainly built into this. We'll do the evaluation of the expression with respect to the environment. But notice, evaluating that thing might itself give us back something that's a delayed thing. If it's a nested combination of pieces, for instance, evaluating the first level may give us back something that is still a delayed promise to get another value. So we'll add one more piece here. We'll add a procedure we're going to write shortly called force it, which says if this expression comes back, make sure I force it to be evaluated all the way out. So that if it returns for me something that is already a basic value, not a delayed promise, I'll return it. But otherwise, I'll go ahead and force whatever is returned as a delayed promise to do the actual evaluation. Keep on winding it all the way through all of the stages until we get back an actual value. Key thing to see, though, is asking for the actual value of an expression, evaluates that expression, and then keeps evaluating using force it until we get down to a base value. As we saw, we'll certainly use actual value inside our evaluator to get the value of the procedure. And we do that because we need to know whether the procedure is a primitive thing or a compound thing in order to be able to keep unwrapping the substitution of unevaluated arguments into the bodies of those things. We also need to use that, though, ultimately when we go off and get the set of values. Remember, in our little lazy apply, if we're applying a primitive procedure to a set of arguments, we need to take that arguments and make sure we get out the actual values of them. List of arg values should take a set of expressions in an environment and evaluate all of those expressions in that environment. And here's how we do it. It's pretty easy. It's a list of expressions. We simply walk our way down the list, getting the actual value of each of the expressions in turn and gluing them together. And remember, applying actual val to one of these expressions will evaluate that expression in the environment. If it returns another delayed thing, it will force it and continue the evaluation until we get out a base expression. So list of arg values takes a set of delayed promises and reduces it to their actual values. On the other hand, if we're applying a compound procedure to a set of arguments, here we want to just take the arguments and substitute them indirectly into the body. But we need to label them as something that is a delayed thing, a promise that says, here's an expression, I haven't done any work on it, but when you actually ask me to do it, I'll evaluate it. List of delayed args then does exactly the opposite of list of arg values. That is, it walks down this sequence of expressions, in order and glues a label on front of it that actually delays it. Creates a promise that says, here is the expression, represented just as tree structure, and here's the environment in which eventually I want to evaluate this expression, and here's a data structure that glues them together that says, I'll do it when you ask me to. Notice, these are the only changes we need to make to eval and apply to implement lazy evaluation. So let's recap what we've done. We've buried a few details we'll fix, but let's recap what we've done. We've changed apply, so that if it is a primitive application, we're going to get the actual values of expressions with respect to an environment. If it's a compound application, we're going to delay the evaluation of the expressions that are arguments until actually required to do them. And eval simply evaluates, when given a compound expression, the first expression to get the procedure out so we know what to do, but passes the rest of the arguments down as delayed things. Ultimately, when we have to do it, in the primitive application, we'll force the evaluation of these delayed things, but otherwise that's it. Now, the only things left are this idea of what does it mean to force it and what does it mean to delay something. So we need to have some abstraction for representing delayed versions of expressions. Well, for historical reasons, we call one of these delayed things, one of these promises, a thunk. And abstractly, a thunk is simply a promise to return a value when it's needed later, or when it's forced, if you like. So it says, inside a thunk, we need to represent the expression itself, the environment that's going to be the context in which we get the value of that expression, and a label that says it's a thunk. And it represents this promise to do the work when asked. To actually implement this, well, we can just build this as a tagged structure, right? We could make a list which has a label thunk at the front, plus the actual expression, represented as list structure, since that's how it's passed into the evaluator, plus a pointer to the environment. And that can be our concrete representation of a thunk, a delayed promise to do evaluation. Well, with that in mind, we can see how we can easily build this. Delay of something simply constructs a list with the tag thunk, the expression, and the environment. Remember again, since expression is just being passed in as list structure, no evaluation is taking place here. It's simply glued together into one of these structures. And then, of course, we have ways of telling whether something is a thunk by checking whether it's a tagged list with the appropriate label, and for pulling out, of course, the expression and the environment that we want to use ultimately to actually force the evaluation. And the corresponding piece is, when given one of these delayed promises, we need to ultimately force it to be evaluated. Here we can be careful. We'll first check to see if this is a delayed thing, a thunk. If it isn't, then we know that this is already down to a basic value. We just return it. This is exactly why we put that label on there, to be able to distinguish between tree structure, for example, that's just part of the data structure being manipulated, from something that actually is being weighted to be evaluated. If, on the other hand, this is a tagged thing that says it's a thunk, we'll get out the expression, we'll get out the corresponding environment, and then we'll do the actual evaluation. We'll use actual value, which we know will force the evaluation of this expression. And notice if the expression on first evaluation reduces to another delayed thing, actual value will force it again and continue to do so until it just returns an object. Well, there are the changes. Very simple changes to our evaluator have allowed us now to build something that does lazy evaluation, does delayed evaluation. We made a small change to apply. We made a small change to eval. We introduced one new kind of thing, a delayed object or a thunk. And other than that, we've done everything we need to do in order to change the way our evaluator works. Notice we now have a dramatic change in behavior based on a small change in the evaluator. As we've said, the evaluator defines the semantics for us, and now we can see this relationship can have very strong effects even with small changes. So what have we accomplished at this point? Basically, we've converted our standard evaluator, our applicative order evaluator, into a normal order evaluator. And to do that, we had to make only a small number of changes in the evaluator itself in terms of things to change in the code. However, we have had to introduce a couple of major new things. The primary one has been this idea of a delayed object. The idea of taking an expression plus the environment in which it's to be evaluated and sticking them together into a promise, a thunk that says, I'm not going to evaluate myself now, but when you ask me for the value, I'll give it to you. And in particular, we've used that to delay evaluation of any of the arguments in procedure applications until we get down to either things that need to be printed, things that are required in order to control the evaluation, or applications of primitive procedures to their actual arguments. One consequence of using these delayed objects as part of our lazy evaluation is that we end up doing, at least at present, some extra work. If you go back to our earlier example, when we compared normal order and applicative order using the foo procedure, you will see that in lazy evaluation, if we used the same argument multiple places inside a procedure body, we had to reevaluate it each time. If this is an expensive computation, we could be wasting a lot of effort. On the other hand, in applicative order evaluation, we evaluated the argument once and then simply used it or referenced it as part of the environment, inside the body of the procedure. So can we trade off this thing? Is there some way of keeping track of values once we have forced a delayed object in order to avoid the cost of re-evaluation? And the answer is, of course, we can. The basic idea is that we'll memoize a thunk. And by memoization, we mean that we'll keep track, using a memo if you like, we'll keep track of when we've actually done the work. So the basic idea is that we start off with a thunk, a delayed expression, an expression that's simply a promise to be evaluated when asked to. When we actually force the evaluation of that thunk, when we do the work to get the thunk's value out, we'll simply remember it. We'll keep track of that by putting a tag on it that says, here's the value associated with this thunk. And then, if the value is ever needed again, we'll just return that value rather than recomputing it. So remember, we've been representing thunks as a tagged structure. It's got a label that says it's a thunk, it's got a pointer to the actual expression, just as tree structure, and a pointer to the environment, which we'll use to help us evaluate the expression when needed. Now, given that this is our thunk, after we've done the evaluation, what do we want to have happen? Well, we simply want to take the result, the value that comes from that evaluation, and keep track of it together with a label that says, I've already done the work. So concretely, we can simply mutate the current thunk into an evaluated thunk by putting that tag on the front together with the result. Notice that we used an important word there in describing that. We said we would mutate the thunk. That, of course, means we're going to take this list structure and actually change its contents. And we can ask the question, why would we want to just mutate the thunk? Why not simply create a new object that says, I'm an evaluated thing and here's my result? And the answer, of course, is if some other part of the procedure or some other part of the evaluation is pointing to this structure, is pointing to this object that is a thunk, by mutating the thunk, those things still point to the same piece. Therefore, I don't have to worry about trying to keep track of who needs this value. I have simply changed the value directly without having to cause any changes to the rest of the procedures around it. How about implementing that idea? Well, it's pretty straightforward. Notice we're taking a particular data structure, a thunk, and we're adding some components to it. In particular, we now have a thunk that can be evaluated, so we'll need to have a way of checking that with a predicate. That'll just be a tag list check to see if the first part of it, the tag is evaluated thunk, is a symbol. And we'll have to have a way of getting the thunk value out of an evaluated thunk, which we'll use by grabbing the right piece of the list structure. This simply goes hand in hand with the parts we had earlier for thunks themselves. Now, you might expect that we should also have a constructor for an evaluated thunk. It seems like we're building a data abstraction here. We've got a predicate and we've got a selector. Where's the constructor? But remember what we said. We said we're going to mutate an existing structure, not create a new one. And that means we're really just adding or modifying the components of a thunk itself. And therefore, we will not have a specific constructor for an evaluated thunk, but we'll rely on changing what happens with a thunk when we force things. Now remember what force it did. It said, given an object, it would first check to see if it's a thunk. And if it was, it would go ahead and get the actual value of the expression part of the thunk with respect to the environment part of the thunk. It would do all the work to reduce it to a value. If it wasn't a thunk, it would just return the object saying that must be the value I want. Here, we need to change things slightly. If the object is a thunk, that is, it has that tag on the front saying, I'm a thunk, I therefore have an expression in an environment, but I have not yet done the evaluation. In that case, we will again do the work to get out the actual value. We will force the evaluation of the expression with respect to the environment. And I'll remind you that actual value would have within itself additional forces to force all the evaluations in case a value that's returned is itself a thunk. As a consequence, we have out the result. Now what we'll do is we'll mutate the existing object. We'll change the first part of the object from the label thunk to the label evaluated thunk. We'll change the next component of the object. Notice the use of coulter of object to get the second part of the list, to actually put in there the result itself, replacing what used to be the expression with result. And then finally, we'll mutate the last part of the object to be the empty list. That is, we will drop the pointer to the environment because we no longer need it. And we've mutated a list of length 3 into a list of length 2 that now has the structure of an evaluated thunk. What else do we need? Well, if the object is itself an evaluated thunk, we'll just return the value. That's what we want from force. It is the value if we have one. And of course, if it's neither a thunk nor an evaluated thunk, it's some primitive thing or some other structure, we'll just return that object itself as the value. And there's our change. We've now gotten the ability to have a memoization version of thunks, which says I'll only do the work once to evaluate a delayed object. So what else do we need to convert our evaluator over to a lazy or normal order evaluator? Not a lot, it turns out. And in fact, to see this, let's think about what we've had to change so far. Our primary change was in apply. Apply now said if I'm applying a primitive procedure, I'm going to go ahead and get the actual values associated with the arguments, because I clearly need them as I'm about to do a final reduction. And to do that, of course, I needed to pass the environment in to help me have that happen. If I was dealing with a compound procedure, I simply took the arguments as expressions and created a list of delayed arguments and put that into the environment. The thunks that basically said, I've got a promise to give you the value when I need it. In terms of eval, we went ahead and said when doing an application, we'll get the actual value of the operator. We need that to know whether we're doing a primitive or a compound thing, but we'll simply pass down the arguments themselves. And then the other changes were ways of actually getting the actual values out for a list of arguments when needed. And we put in this last little piece of memoization, which is basically an efficiency issue. Now, what else do we need? Well, the other change that we need is in one of our special forms, and that's in if. Think about what happens in an if. Here, in order to decide which direction I'm going to go, I need to get the actual value of the predicate. I can't make a decision if I don't know. If it's just a promise to say, I'll get you the value when you need it, I have to make a choice. And so within if, I will go ahead and get the value of the predicate part of the expression. But the other components I can simply pass along as thunks, relying on the reduction to basic forms or to primitive things to eventually get out the value I need there. So one small change inside of if. And of course you can see what I'm doing. I'm working my way through now the special forms to decide are there any changes I need to make there. I've changed application, only the special forms remain. If is one that I do need to change, but the others I don't. For example, think about an assignment. If I'm going to do an assignment, a set bang of something, do I need to make a change here? And the answer is no. I can still go ahead and get out the variable. That's the part of the expression anyway. But in terms of what I put in as the value associated with that variable, I can go ahead and do lazy evaluation. If I don't actually need the value yet, I'll simply store it away as a thunk. If it's already been evaluated, I'll store it away as an evaluated thunk. And otherwise, if there is a value there that was other than one of the thunks, I'll put it in. But I don't need to actually change what I'm doing inside of assignment. And that basically completes our conversion of our evaluator from applicative order to normal or lazy order evaluation. One of the goals of this particular lecture was to show, as we've done in some earlier lectures, how we can change the behavior of a language, the behavior of a programming environment, by changing the evaluator. And in particular, how small changes in the evaluator can have very large consequences in how something happens within terms of the evaluation of expressions within that language. Here we've converted from an applicative order to a normal order or lazy evaluator. One of the questions we can ask, though, is what are the trade-offs in terms of impact on the language? And with lazy evaluation, we actually have an interesting dilemma. On the one hand, we have a real plus. We only do work when we need an actual value, which means in principle we could come up with very efficient ways of programming things. On the other hand, we're not always certain when an expression will be evaluated. And if we've got a language with side effects in which mutation takes place, this can be a serious issue. It can both lead to conceptual errors as well as programming errors and can cause us some real difficulties or disadvantages. It may also be the case that we evaluate the same expression more than once. Since we're delaying the evaluation, we don't know when it's going to be evaluated, we may end up redoing work. Well, some of this we can fix with memoization. It allows us to evaluate an expression at most once and resolves this issue of doing extra work, but it has the disadvantage that we don't have control over it. What if we want evaluation on each use? What if the evaluation of an expression in fact involves, say, mutation, in which the side effect is important, and it's not the value that's returned, but the effect that takes place that matters? In that case, we want to be able to do this, and as we've structured it so far, we don't have that ability. So this makes it sound like lazy evaluation isn't a good idea. And of course, that's not true. It's really a trade-off. One way of approaching this would be to say, gee, if I'm going to have no side effects in my language, I'm not going to allow any mutations to take place, then lazy evaluation may actually be a very powerful thing to use. With memoization in place, I can have efficient implementations, only get values when I need them, and have my code run as I would expect. But of course, if I want to have side effects or mutations, then I have a disadvantage. I don't know how to control when I get the evaluation out. Well, we've got another alternative. We could give the programmer direct control. We could let the programmer specify, do I want something to be a thunk, a delayed promise, or do I want something to be a value directly? And let the programmer make the decisions about how to make that happen. The question then is, how do we build that into an evaluator? Well, let's change our evaluator to let the programmer directly tell us what he or she wants. In particular, will let the programmer specify when they create a procedure whether a variable should be treated as a normal variable, as a lazy variable, or as a lazy memo variable. Here's the form we'll use. We'll now let lambdas have as their parameter lists of just variables, or expressions that say here's a variable name and here's what kind of thing it is. In this particular example, we'll treat A and C, or we'd like the evaluator to treat A and C, as normal variables. When we apply a procedure, the arguments associated with this should be evaluated before we actually do the procedure application. We'll specify that B is a lazy variable. That says when an argument or a value is passed in for this argument, it should get re-evaluated each time its value is actually needed. It's a delayed thing, but every time we need it, we'll go ahead and do the value. On the other hand, we're going to specify with this example that the argument D should be a lazy memo value. That is, when something is passed in as part of an application of this procedure, the argument will be evaluated the first time its value is needed. It'll be delayed up until then, but then that value is just returned again any other time that it's needed. This will allow us to distinguish between things that we want to get evaluated right at procedure application time, things that we want to delay until we actually need them, but reuse or reevaluate rather every time because it may have a potential side effect in it, and things that we want to delay the evaluation of until we actually need it, but having gotten it, we can just keep track of it. So notice what we're doing. We're now giving the programmer the ability to put declarations on the variables or parameters that are part of a procedure, saying something about what kind of behavior we want there. This suggests that one of the changes we'll need to make to our evaluator is to change the syntax. We now have to change the syntax associated with the lambda expression. And a lot of this is pretty straightforward. So remember what happens in our little lazy evaluator. When we go to apply a compound procedure, the thing we're now changing, we evaluate the body of that procedure in an extended environment. And what did the extended environment do? It took the list of parameters from the procedure definition itself, plus a list of delayed arguments, and glued them together. Now we have to think a little more carefully about what does it mean to actually look at the list of parameters. Well, remember, in the full-blown version of a lazy evaluator, list of delayed arguments, the thing that created the arguments, would simply delay everything in the list of things passed in. Here, we want to walk down the parameter list at the same time we're walking down the arguments to decide, do I want to evaluate it or not? So, we can build some structure to do that. We'll need a way of getting the next variable out of the list of variables in the parameter list, as well as the rest of the variables. And we'll need a way of checking for each one of those whether it's just a symbol, which means I want to get the value directly, or whether it's something that has been declared to be of a particular type. So declaration question mark will simply check to see whether the next element in the parameter list is itself a list or not. To get the actual name out of one of these variable declarations, we'll check. If the thing is a pair, then we know in fact that the first part of it will be in fact the name, as we saw in our previous example. If the object is not a pair, then it's not being declared to be anything, we just return the name itself. And of course we can check to see whether something is lazy or whether something is a memo by making sure that it is a pair, that it's a declaration, and then checking for the tag. So this will allow us to walk down the parameter list associated with a procedure, something we built with a lambda, checking each element in turn to decide what's the name of this variable and does it have a particular declaration on it saying it's either something that's a lazy evaluation or a lazy memoized evaluation. In terms of the values to be associated with variables, we now have several different flavors. We have standard values, numbers, symbols, other such things that have been reduced down to their basic primitive form. We also have thunks. And thunks, as we've said, will be something that does not ever get memoized. It will be labeled as a thunk, and it will be simply treated as a thunk. This means an object in this particular version, labeled as a thunk, will always be reevaluated whenever we ask for its value. We never keep track of it, we simply represent it as a delayed promise. We will also, however, have a memoized thunk. This is a different declaration. And here the idea is that when we first evaluate this thunk, we're going to remember it. And we'll remember it in a particular structure. As we did earlier, we'll mutate a thunk memo structure into an evaluated thunk, keeping track of the results. So when we actually force the evaluation of one of these thunk memos, we'll convert it, mutate it, into this new structure. Notice what we're doing now. We're making a distinction between a thunk and a memoized thunk. In our earlier version, we always memorize thunks. Here we're allowing the programmer to specify. If he says something is going to be a thunk, it simply remains as a delayed promise. And every time I want to get the value, I redo the work. If the programmer specifies it as something to be memoized, when first evaluated, we will do the work to get the value out. Prior to that, it's simply a delayed promise. But having done the work once, we'll mutate this structure into an evaluated thunk, keeping track of the results so we can simply use it whenever we need it. Now remember, in our full-blown version of a lazy evaluator, the key issue came when we actually went to apply a compound procedure, because we glued together the parameters of the procedure with a list of delayed arguments. We delayed each argument, putting in a promise to get the value when necessary, and then putting that into a new environment and letting the evaluation of the body take place. Because we're now giving the programmer some control, we have to re-examine delay it. And in particular, we need to make a small change. Previously, delay it would have simply taken in an expression in an environment and delayed it. That is, converted it into a thunk. Now, however, we need to pass into delay it not only the expression that potentially is to be delayed, but also the declaration, the part of the parameter list that corresponds to this expression. And we'll do the following. If that parameter is not a declaration, if it says it's just a plain variable, then we go ahead and get the value right now. That's exactly what we want. Get the value and return it. On the other hand, if this variable has been specified by the programmer as being lazy, we will then convert it into one of these delayed objects. We will create a structure with the name or symbol thunk and the expression in the environment, exactly as we would have done in the normal case. On the other hand, if it's specified as something we want to memoize, we'll similarly label that with the distinctive memo that it's a thunk memo and glue that together with the expression in the environment. So now see, we're using the declaration itself to tell us what to do. Whether to delay the evaluation of this expression or do it now, and if we're going to delay it, which kind of delay we want. Similarly, because I now have different kinds of expressions floating around in my system, I need to also change force it. Remember, force it was something that would take in an object, and in the previous version, actually force the evaluation of the object if it was delayed, and if it wasn't, simply return that value. Here, I've now got a set of things I want to deal with. First, if the object passed in has been labeled as a thunk, a delayed promise, I get out the expression part of the object, the environment part of the object, and do the work, get the actual value, forcing the evaluation of this expression. And I'll return that value as the value of this object. But notice, I don't remember it. I'm going to have to redo the work again if I have another place that wants to use this thunk. That's the behavior I said I wanted. On the other hand, if this is a memoized thunk, it's got that label on it, I will again get out the expression and environment, do the work to get the actual value, and then having gotten that value, I will mutate this structure to label it as an evaluated thunk with the right result. And remember, I'm mutating in place so that anything that points to this object, that has a pointer to this actual structure, will still have a pointer to this structure. We've simply replaced a promise to do something with the actual value and a label that specifies that. If something has already been evaluated, I just get the value out and return it. That's all I want. And everything else I just return straightforwardly. And with that infrastructure in place, I can now go off and make the key change. In apply, or in lazy apply, under this version now, I want to simply keep track of what I want to delay. I'm only going to delay parameters that are specified as being lazy or lazy memo. In the case of a lazy parameter, I'll make a thunk out of it. In the case of a lazy memo parameter, I'll make a memoized thunk out of it. And that we see will happen by simply our new implementation of delay it. What else do I need to do? Well, basically, when I go to apply a compound procedure, I need to do the following. When I apply a compound procedure, I once more want to evaluate the body of that procedure with respect to a new environment. And that environment I'm going to get by, of course, extending the procedure's environment with a new frame. But in that frame, notice what I'll do. First, I'll get out the parameters that correspond to the procedure, just pulling out the list structure. But now I know that that list isn't just a list of names. It may be a list of names and declarations. So to extend the environment, I need to get just the names themselves, which I do by mapping parameter name down that list, pulling out the names. And then from the parameters, I go ahead and create the set of list of delayed arguments by taking those declarations together with the arguments passed in and using delay it to walk down the list and decide, do I evaluate now, do I create a thunk, or do I create a memoized thunk? There's the change we need. And now I can use all the infrastructure I put together to create that actual list of delayed arguments. I simply take the declarations, the list of variables and their declarations, plus the list of expressions, the arguments passed in, and walk down those two lists in unison, delaying each one. And remember what delay it will do. It will look at the declaration to decide, is this something I want to get a value of right now, in which case I'll do it? Is it something I want to turn into a thunk or a memoized thunk, in which case I'll do the appropriate delay? And doing this now allows us to control when we evaluate. Do we evaluate on application? Do we evaluate when required? Or do we evaluate and remember and simply look up when asked for? So what does this do for us? Well, now we've built in some programmer control. By changing how we deal with the arguments when we get to an application, by deciding at that time, do I evaluate, do I delay but keep track of, we've now enabled the programmer to specify what he or she wants. When they create a lambda, they have the opportunity to say, I want the values of this parameters on application time. Or, I want the value of this parameter delayed until I need it, but I'd keep doing it every time I need it because I may be relying on side effects or other things inside of that evaluation. Or, I want to delay this until I absolutely need it, but once I've got it, just keep track of it so I don't redo that work. We've built in now programmer control. The key thing to see is how, given this idea of lazy evaluation, we're able to easily change the performance or the behavior of our system. A little syntactical change in terms of how we specify parameters and a little change in the manipulation of the evaluation itself gave us a very different performance. So as we've seen then, we now have the ability to really change the way an evaluator behaves. We can control the order in which things are evaluated, going from an applicative order to a normal order, or to things in between. We've also seen that those changes involve only details of the evaluator, and in many cases very small details. And they allow us to have models of one kind, models of another kind, or models of evaluation in between that let us control as a programmer how we want the evaluation to actually take place. Now, let's look at one example in which changing the evaluation model allows us to explore a very different kind of computational problem. Our goal is to show how a small change in the evaluator, basically our lazy evaluator, can let us have a very different way of thinking about programs and programming. Imagine that I want to simulate the motion of an object in a complex environment. A simple case might be a tennis ball that I throw against a set of walls. I would like to simulate how the ball would bounce against those obstacles and where it might end up. In our earlier approach, we might have chosen to model this using an object-oriented system, which seems like a natural way of breaking this problem up into pieces. Under that view, we would have a different object to represent each different structure in our world. We might have an object that represented the ball with some internal state that captured the properties of the ball. Similarly, each wall would be an object, perhaps with different characteristics representing how objects bounce off them. And we might have a clock to synchronize interactions between the objects, leading to an object-centered system very similar to what we saw earlier. In this way, each synchronization step would cause the objects to update their state, including detecting when, for example, two objects have collided, so that the physics captured in each object would then govern changes in the state. The thing to notice is that while this is a natural way of breaking up the system into units, the state of the simulation is basically captured in an instantaneous way. At any point in time, we can determine the state of the overall system by the values of the state variables of each object. But we don't have a lot of information about how the system has been evolving. Said a different way, by breaking up the system into units of this form, we are naturally focusing on the discrete objects within the system, not on the behavior of the system. There is a very different way of thinking about such systems, however. Rather than having structures that capture state explicitly, I could think about systems in which the state is actually there only in a very implicit way. In my example of a tennis ball being thrown up against a set of walls, imagine that while I'm doing that, I actually place a set of cameras around the room that are recording the movement of the ball and as a consequence capturing the information about where the state of the ball is. In particular, imagine that this is happening in a continuous fashion. There's a constant stream of information being spewed out that represents the X and Y position, for example, of the ball as it moves around the room. Under this view, my basic units now become the time series of values of the different variables that represent my system. In the earlier version, my basic units were the objects themselves, the ball, the wall, the clock, anything else. Now, I've changed my viewpoint. I've pulled out the state variables and said my basic units are the stream or history of values associated with them. To capture the state of the system at any point, I simply take the values of all of those variables across the same point in time. But my units now that I want to think about are the actual history of values, the stream of values associated with each thing that represents my system. A key question then becomes, how can I efficiently capture this information? And an obvious thing to do is say, well, just represent it as a list. Just keep gluing new values that represent the state of these variables onto the beginning of a list as I go through my simulation. And while that's an appropriate way of thinking about it, we'll see that once we start getting into complex systems, it becomes very difficult to do this efficiently. We'd like to have a way of capturing that information without having to do excess computation. And for that, we're going to turn back to what we did in the last lecture. Now, we just saw how to convert our standard, or applicative order evaluator, into a normal order or lazy evaluator. I want to take that idea and use it to change the way we think about programming by showing how changing our viewpoint on evaluation, coupled with this idea of capturing objects by their streams of values, gives us a different way of programming. The key ideas we're going to use are the notion of deferring evaluation of sub-expressions until only when needed, and the idea of avoiding re-evaluation of the same sub-expression by memoizing. So we created an evaluator in which the programmer could declare, when building a procedure, how to treat the different parameters. In this little example, A and C are normal variables, meaning they will be evaluated, or their arguments will be evaluated before we actually apply this procedure. B we treat as lazy. That says we don't evaluate the argument expression passed in when the application is done until it's actually required somewhere inside of the body when a primitive procedure is applied. In that case, it is evaluated and the value is used, but it's thrown away once we're done. And any other time that this parameter is used, we'll re-evaluate the sub-expression to get its value out. And finally, D we could mark as being lazy but memoized. That means we don't evaluate it until required in the body of this procedure when a primitive procedure is applied to it. When we do actually do the evaluation, however, we keep that value around, remembering it for subsequent uses of this actual variable somewhere else within this procedure. So how could we use this idea in our context? Well, we could create a new data abstraction called a stream. Here's one particular version of it. It has a constructor we'll call constream, and it has two selectors, stream car and stream cooter. You can see by the names that they're going to behave a lot like what a list would, except for the following. And the following is that the second part of a constream is lazy, or rather lazy memoed, meaning I am not going to get the value of the second part of this structure until I'm asked to. But having been asked to, I'm going to store the value away. Here we've chosen to represent it as a message passing system. You could imagine we could also just do this using const directly. The key change, though, is now I have a way of constructing together or gluing together a sequence of values in which only the first value is explicitly evaluated when I do the construction. The second part of this structure is lazy. It's a promise to get the value when asked for it, but I don't do the work of actually computing it. Now, what does this do in terms of thinking about building long sequences of structures? A stream object, thus, looks a lot like a pair, except that the cooter part is lazy. It's not evaluated until actually needed, and when it is, we'll keep track of that value so we don't have to redo the work. Think about what happens now. For example, if I ask x to have the value of a const stream of 99 and divide by 10, what will happen? Well, if I did this just using a normal const, not const stream, I know what will happen. I'll get an error because const would say evaluate its two arguments, getting the value 99 easily, but then trying to divide by 0 and ending up with an error. In the case of const stream, I can do this safely because const stream will evaluate its first argument, the 99, but will simply create a promise to evaluate the second argument and glue the two things together. As a consequence, x is safely defined, and I can get out the car of it as a stream, returning the value 99. It's only when I go to actually get the cooter that I will do the evaluation and end up with the error. So what we see is there's now a nice difference between a stream object as a pair and the standard pair, in that the second part of the stream is not evaluated until required. What we're going to do now is build on that idea to see how we can create very different structures and different ways of thinking about how we do computation. This may seem like a very straightforward change. What I've done in essence is say, given my standard way of gluing things together, consts, let's make an alternative in which I glue together the value of the first thing with a promise to get the value of the second thing. It doesn't sound like a lot, but in fact it has a very fundamental impact on how I can think about computation. In particular, I can now decouple the actual computation of values from the description of those values. Or said a different way, I can separate out the order of events that occur inside of the computer from the apparent order of events that are held in the procedure description. And let's look at an example of that. Suppose I want to find the 100th prime value. Well, here's a standard way in which I could do that using list processing, the ways we've been doing things prior to this. I could use enumerate interval, which we saw several lectures ago, to generate a list of all the integers from 1 to 100 million or whatever. I could then filter that list using something that checked for primes. There's a version of it in the textbook. I don't really care what it does. I simply want to think about the idea of filtering that out. And then I could go in and find the 100th element in that list. Notice what I've done here. I've first had to generate a very large list from 1 to 100 million because I'm not certain exactly what values I'm going to need. The key point is I've done a lot of computation and I've created a very large data structure. Filter will then run down that list and generate a new list, not quite as long but still very long, in which it checks each element in turn, throwing away the ones that it doesn't want and keeping only what's valuable. And finally, list_ref will simply walk down that list, find the 100th element, keep it, and throw everything else away. In this way of viewing things, I have to do all of the computation to get the value of an expression before I can move on to the next stage. And it literally says I have to do an entire generation of a data structure, then pass it to another procedure which does an entire generation of another data structure, and then passes that on. Clearly in this case, it's wasteful because I don't need those entire lists. Suppose instead I change my viewpoint and I say, rather than creating an entire list of all of the integers before I can do any filtering, I'm going to create a structure that has the first integer I want and a promise to generate the rest of the integers when you ask for it. That says rather than creating enumerate interval as a big long list, I'm going to use streams. And streams will say, because of that lazy memoization, that when I ask for the intervals of the stream from A to B, I will generate a structure that gives me the value A, as the first part of const stream, and a promise to generate the rest of the interval when required. I can certainly imagine creating a stream filter that behaves just like filter did on list, but uses const stream and stream car and stream cdr rather than const car and cdr. And now notice what would happen. In this case, when I evaluate the bottom expression, stream interval will generate a structure with the value 1 and a promise to generate stream interval from 2 to 100 million. That can instantly be passed to stream filter, which will now check the first element. Since 1's not prime, it will throw it away and ask for the next element in the stream. Stream filter, remember, is going to walk down the stream. This will now go back to stream interval and say, please generate the rest of your stream, which will cause const stream to generate the value 2 and a promise to generate the rest of the stream. And as a consequence, these two procedures will work in synchrony. Stream interval generating the next element of the stream, passing the entire structure to stream filter, which will keep looking at them and will pass out values as they come along to stream ref. As a consequence, we will only generate as much of this stream of values as we need until we return out the 100th prime. Notice what this has allowed us to do. We can now think about the processing as if the entire set of values was available. We're thinking about how to deal with streams as if all of those values were actually there. But in fact, when we go to do the computation, the laziness allows us to in fact separate out the order of events inside of the computer from this apparent order of events in the description, so that we get the efficiency of only computing what we need while allowing us to think about things as if the entire structure, the entire sequence of values was available. If we go back to our little motivating example at the beginning, it says we can think about building simulations in which we think about the entire stream of position values as if they were available, but we don't have to do all of that computation in order to actually run the simulation. To see how this lazy evaluation gives us this kind of behavior, let's look at this in a little more detail. So first, here's one of our procedures, a standard stream procedure that we write. This looks just like our filter that we wrote for lists. The only difference is we're using the stream data abstraction. So we're using stream car and stream cdr to get out the pieces, and we're using const stream to generate out the structure that we want to get. Let's see, though, how the lazy evaluation in const stream allows us to separate out the order of evaluation within the machine from the apparent order of evaluation as described by the actual procedure. Indeed, a standard question might be, why doesn't stream filter end up generating all of the elements of the stream at once? The answer is here. When we apply this procedure to a stream, it will recursively test each element in the stream until it finds one that satisfies the predicate. At that stage, note what happens. We generate a stream with that element as the first element and with a lazy or delayed promise to filter the rest of the stream when needed. Thus, we generate the first element of the new stream and just a promise, not the So let's look at what happens with our little example. We're going to filter the stream of integers from 1 to 100 million using prime. And let's see what would happen if we actually do this, looking carefully at how lazy evaluation controls the order of evaluation. Well, stream filter is just a standard procedure, so we need to get the values of its arguments. Prime will just treat as some procedure, but stream interval we need to evaluate. Notice, however, stream interval, as you recall, was defined in terms of const stream. So it literally returns one of these stream objects, which has the value of the first element, 1, already available, plus a promise, shown in that squiggly line, a promise to get the value of the next argument, which is stream interval from 2 to 100 million. Now, notice at this stage, all that has been explicitly computed is the first value. Everything else is sitting around as a promise. Having evaluated the two arguments appropriately, we can now execute stream filter. And notice what it does. It applies its predicate to the first element of the stream car. 1 is not prime, so in this case, stream filter says the value to be returned is to call recursively to stream filter with the same predicate, but on the coulter of the thing that was passed in. So now we're going to force that promise that stream interval from 2 to 100 million is going to be asked to do its thing. Now here's where a potential confusion can arise. It might seem to you like when calling stream interval, getting the stream coulter of that piece takes place, that it should now run off and generate everything in that entire stream, all the elements of the list from 2 to 100 million. But in fact, we know what stream interval does. Stream interval says, do a const stream of the first thing onto a promise to do the rest. So in fact, it returns another stream object with the next element now available and a promise to do the further things. And that is what will be then used as part of stream filter. So now stream filter can evaluate its body, or apply its procedure, if you like, to its body, testing with the predicate to see is the first element of this stream a prime. It is, so it returns a const stream of, the first element, which is the 2, plus a promise. And the promise is to do a stream coulter on the remaining, or rather a stream filter on the remaining things. So notice what this stream filter is. It's a promise that says, when you ask me, I will try and filter using prime on a stream coulter of the object I started with. So we now have two delayed promises. We have a promise to do the filter, and inside of it is a promise to go off and get the rest of the stream. This now lets us see that we will, in essence, only pull out values as needed from this stream filter. If we were to ask what's the next element in this sequence, we'd go past the 2 and force the evaluation of stream filter, which would force the evaluation of the stream coulter and pull out the next prime. Nonetheless, we'll only, in essence, tug on this stream to get the next element when requested. But by building our procedures, both our filters and our constructors, using const stream, we actually separate out the order of evaluation from the apparent order of evaluation. Now we see that if we create procedures that manipulate this stream object, this new data structure we have, we never have to worry about how long the data structure is. We only get the next element in order as we ask for it. And this raises an interesting question. If we don't really care about how long the rest of the structure is, how long can we actually make it? And the answer is, well, infinitely long. Or that's a slight misspeaking. Let's just say indefinitely long. But we can now, in fact, create data structures that have arbitrary length and act as if they had infinite length. And this leads to some really interesting behavior in terms of how we think about processing. So let's look at an example. Let's give the name ones to the structure we get by const streaming the integer 1 onto ones itself. Okay? That's going to make a weird looking little structure. And in particular, if we ask for, say, the second element in this stream, we get out a 1. Why is this happening? Well, defining it this way says the name ones refers to or points to a structure created by const streaming the integer 1 onto a promise to get the value of the name ones when asked for it. And that says when we ask for the stream coulter of this object, we will at that point evaluate ones, and it will go back around and point to this same structure. And as a consequence, this structure basically represents a very funny thing. It represents an infinite stream of ones. No matter how many times I ask for the next element of this list, I will always get out a 1. So I now have a structure that I can think of as representing an infinite set of things. Whenever I ask for a particular element of that thing, the 100th element, for example, of this structure, I will get out the thing I want, namely a 1. This may still seem odd, so let's think about the comparison. Suppose I did define ones to be a const of 1 and ones. Of course, in this case, I get an error, because remember, const requires the value of both its arguments before it can actually create the structure. And I don't have a value for ones yet, so I can't, in fact, do it. Streams, though, with the lazy evaluation, enables me to hold off getting the value of the second element until I've completed the structure, which means that the name ones will be available to me when I need it. So now we see lazy evaluation gives me the ability to create one of these infinite data structures. So what does this buy us? Well, this way of thinking about infinite data structures, in fact, lets us think about creating procedures that operate as if the entire data structure were available to us on demand. So for example, things that would typically apply to lists, procedures that might handle finite lists, we can now turn into procedures that handle infinite streams. To add together two streams, for instance, we could have something that checks to see if either stream's empty, in which case we just return the empty stream. Otherwise, we'll use our data abstraction to constream the sum of the first two elements onto whatever we get by adding the remaining streams together pairwise. The idea would be to take two infinite streams, add each of their elements up together, and create out a new infinite stream. Using this, for example, we can create the infinite data structure of all the integers. We simply constream the first integer, which is 1, onto whatever we get by adding together the stream of ones to the stream of integers. Now, let's check it out and make sure this does the right thing. So what does ints, or integers, look like? Well, we know the first element will be a 1 because we constreamed that onto a promise to get the rest of the integers when we want them. Okay, suppose we now ask for the second element of this stream. Well, the second element was a promise. A promise, because of the construction of using lazy evaluation, a promise to add together the streams of ones and the streams of integers. So to get the second element, we now need to evaluate this. Notice, though, that at this point, both ones is available. We know that's just an infinite stream of ones. But also, the stream ints is available as the first element plus a promise. And since that first element is available, that allows us to go ahead and ask for it. And add streams will therefore constream the first element of ones and the first element of ints together, and add those up, generating that as the first element plus a promise to do add streams of the remainder of these two streams. If we were to ask for the third element of ints, we would then force this promise. We would force the promise that says add together the streams of, a promise to go off and get stream coder of ones and stream coder of ints. That says if they have not already been evaluated, we'll do them. But if they have, we'll keep them around and generate out one more element. So this says we can basically walk our way down integers. Whenever we ask for the next element, it will tug, if you like, on the stream of ones and use the previous values of integers that it has created to create the next element, plus a promise to create the remainder of the stream. And we can continue this all the way along. Having the ability to create these infinite data structures, the infinite stream of ones, the infinite stream of integers, lets us actually change our way of thinking about things. In particular, remember the sieve that we saw several lectures ago. This was the sieve of Eratosthenes that said to find all of the primes, start with the integers beginning at 2, and do the following. Take the first integer, or the first element of that list, keep it because it's a prime, and then remove from all the other structures, or all the remaining elements, everything that's divisible by that number. Then move on, take the next remaining element, keep it because it's a reprime, and remove everything divisible by that. And we walked our way along generating the list of primes. But remember, to do this, when we had just lists, we had to create a list of integers from 1 to some point, and then process each of them in turn to make this thing happen. And in particular, that said, we had to first generate the first element, then filter everything else in the remaining list. That is, literally create a huge long list of all the things that were not divisible by 2, keep the next element, and then filter or remove all of the elements of that list. This again had this property that we were generating lists, filtering them, generating lists, filtering them, and doing a lot of extra work. We can now turn this around. Using the idea of having infinite data structures available lets me create a sieve that in fact is much cleaner than the list version. Remember, in the list version, I'd have to generate the entire list of integers, then filter that to generate another list of everything that's not divisible by 2, then filter that to get another list of everything that's not divisible by 3. I'd have to do a lot of work to create the elements, the primes. On the other hand, with infinite structures, I can generate the primes only as needed. Notice what I would do. I can create a sieve that says, given an input stream, I'm going to generate an output stream. The first element will be the first element of the input stream. The rest will be a promise. A promise to do what? Well, to take the rest of the stream, stream coder, filter it, removing everything that's divisible by the first element, and then taking the sieve of that. And ooh, that's nice, because that sieve will then, when asked to be evaluated, forcing the promise, will generate the first element of that filtered stream, plus a promise to sieve again. This says, as a consequence, I will only pull out those elements from this sieve that I need on demand. I can think as though the entire stream was available, but actually do the work increment at a time. One element as needed, then the next element as needed. And as a consequence, I can define primes to be the sieve of all of these integers starting at 2. Notice, by the way, that in this sieve there's no base case. There's no test for am I at the end of the stream. Oh, that's okay because our streams are in fact infinite, and we don't need to worry about that. We'll simply keep generating more and more promises to get future elements as needed. But here we have no base case and no test for a base case. We simply have the construction of the stream element by element. In fact, this idea of thinking about these stream structures as infinite sequences of things that are just in existence or are generated, if you like, as needed over time, relates very nicely to a way of thinking about programming that's somewhat different. Indeed, stream programming looks a lot like traditional signal processing, the kinds of things you'll see in 6003, for example. And what does that say? Well, if we were to think about processing an audio signal, for example, a standard way of doing it would be to say that we have some signal coming in, an initial value x. And what we're going to do to generate an output signal y is take x, delay the signal slightly, amplify it, run it through something that increases its value by some factor g, and then adds that value back in. This is a standard little feedback loop in which we get an output signal by processing an input signal, modifying or amplifying it to scale up the values. Now, we can do the same thing using streams. We can capture this idea of signal processing very cleanly. So we can capture this idea of a feedback loop very nicely in streams. If x is our input stream, we'll generate an output stream y as follows. X, the first element of x, will simply pass through. But to get the next element of y, we'll take the second element of x using stream coder, which is equivalent to doing a delay, map that through something that scales the element of the stream, meaning just multiplies it by some constant, and adds it to the value of x that's coming out. So we're going to take a delayed version of x, scale it, and add it to the initial version of x, generating as a consequence an infinite stream as output. Now, why would we like to have that? Well, that leads to a very common example of a feedback loop. In fact, exactly that idea of a feedback loop can be used to build an integrator. What would we like to have if we had an integrand represented as a stream of values? You can think of that stream as tracing out a curve, and we want to get the value of the area under that curve. Well, we could generate a stream that outputs the values corresponding to the integrand. And what would that look like? Well, whatever the first value would be some initial value, for example, 0. And then to get the next value, the value under the curve so far, what should we do? We take the stream of input values, scale them, multiply them by some constant dt, which is the spacing between the values, and then add that value to the value we have so far. And why does that make sense? Well, we're adding the area under the curve as we move along. And so we can simply generate a stream as needed, in which we take the value of the previous point in the stream, which is the value of the integral so far, and add to it the area under the next step. For example, we could use this to generate the integral of the stream of 1s. If we take the integral of the constant value 1 with a spacing of 2, so our dt is 2, notice what will happen in terms of this constream effect. Int is returned as the actual stream, and if we look at the first element of it, it's just the initial value, in this case 0. The next value in this integral stream is given by adding together the scale stream of the integral with whatever we've done so far. And what does that say to do? We say take the value, the first value of 1s, scale it by 2, and add it to the first value of the integral so far. Those two simply get added up to create a 2 plus a promise to get the next element as we need it. And of course, if we ask add streams to evaluate its next chunk, it will take scale stream of 1s, multiplying it by 2, plus the element we've added so far, add those together and generate 4 plus a promise to carry on, and so on. So the key points to note are that by having this idea of lazy evaluation, we can create structures that will provide promises to create the remaining elements when needed. And then secondly, we can use those ideas to think about those structures as if they were entirely available when creating procedures to manipulate them, yet have the actual evaluation occur just in time to provide the value that we need.